Good afternoon, everyone. Welcome on this beautiful summer day. This is the first lecture in both the biomedical optics and the light interaction. The first 3 weeks of these courses was in parallel. So they are basically 2 different courses. They have common foundation, and both will be about medical imaging or diagnostics that is based on the interaction of light with biological tissue. So we will study state-of-the-art state-of-the-art biomedical optical techniques. Then we will also study some of the physics of the main interactions. Absorption Spectrum. First subject, and the emphasis on like this interaction. This is the so I will start with some household stuff to know what to expect for now. The first 3 weeks will be together. These are the topics that we will discuss. We will discuss absorption today and scattering on Friday. The multi-parallel methods and multiple light scattering, the regards to that. And then there was Boer takes over, who will give you an introduction on optical tomography and Roman spectroscopy. Yes.
I know I'm sitting in the back, but I need a charger. Could you maybe turn off the first light because I cannot really read it?
Yeah, I think so.
Yeah, that's always better.
Thank you. Yeah, so this is the schedule for the first week. Then after that, biomedical optics continues with topics by guest lecturers. So Martijn will give you an overview of clinical OCT, and for radio scattering, festivals, and the light tissue interaction course that dives a little bit deeper into the physics. So that's roughly it. We will have 2 classes per week, pretty long sessions. Often almost. So more or less it will be. We'll hope to engage a little bit in discussions about the topics that we had so far. So I'm not the only one talking all the time. There will be, of course, some lecture parts. I will be talking. We will have some in-class assignments, so just practice assignments. Graded. Will be time to work on graded assignments. That brings me to the next slide. Your grade, your final grade, will be composed of 3 written assignments, which you can make individually or in a small group. That's okay with you. And an individual exam, a written exam at the end of the course. So that's one you have to make home. They all count for 25% of your grade. But for the individual exam, you have to have plus the customers. After that, we calculate the of the assignments. Please submit all everything 5 canvas because that is the only way for me to really keep track of this. I will set some due dates. The first assignment will be the same assignment. They all in groups. Second and third assignments will be different. I'll hand it out on next Friday, and it will be due after this first. You know what you can expect. So we'll do this hopefully in person as long as we are able to and allowed to. So we never know what happens with COVID. We will know what happens with the trains because they don't run on Friday. So that could be maybe a problem for some of you. I don't know. The idea is to record all these lectures, to have a Zoom meeting running in parallel. So if you cannot make it, YouTube video would be so useful. Try to join by Zoom. Otherwise, it will be recorded. Always look at it. The materials and the announcements go via text, so please make sure that you can access the course pages. And the other stuff, I will post the recorded lectures on YouTube. The link to the have a quick version in comments. All right. If you need to contact me, preferably via campus, you can mail me on any of these two addresses. I'm pretty small. If there's a really urgent matter, please send me that. All right. Any questions about this organization? Okay, then we'll slowly migrate towards the content. This was in the news last week, saying that the chances of survival of cancer after diagnosis are increasing. It's a trend that is ongoing for several years now. And the table there shows in a little bit complicated way that people with certain types of cancers have even better, increasingly better chance of survival. This is of course due to progress. We have better techniques finding the cancers early. If you find it early, it means you have better prognosis for treatment. And otherwise, fortunately, the health, the general health, is also increasing. So it is good news. That is good news, but because it puts challenges on the healthcare system. If there are more people surviving with cancer, so people are not necessarily cured, these patients are living longer with their cancer, which doesn't mean that they will have to keep receiving the care. So the combination of an aging population, with earlier diagnosis and better treatment, leads to more patients requiring longer treatment. And that can have a big impact on the cost and just the manageability of that. Then there's the second thing, that's policy ambition by the government. They have formulated policy that by 2040, in less than 30 years, all Dutch citizens will at least live 5 years longer in good health. That compounds to the numbers as well. And then also there's socioeconomic policies all not big spot here. This will put a burden challenges on sustainability. So because of that, of course, people realize that, and because of that, there's a lot of research going on in innovation, in technology in healthcare, seeing if we can shift care from the hospital to the home, if you can invest in prevention, those kind of things. But for all these applications, we would like to be able to keep an eye on the patient, to keep monitor the patient. So the technology that is being developed throughout now, it's aimed at these changes, at these fundamental changes that are going on in healthcare. So if you look at healthcare now, at patient care, and imaging is really a cornerstone factor. Seeing PET images and MRI images every diagnosis basically starts with the image. There we run into some limits because current radiological methods, they do not reach cellular resolution. So the resolution of these techniques is about millimeters or centimeters, the smallest structures that you can resolve. And they have limited molecular specificity, which means you can make images of morphology, but you cannot necessarily very easily visualize what is going on in the record. So that means that even with the sophisticated techniques, sometimes we are still too slow identifying these things, which makes it more difficult to prevent it. So this then is the niche for biophysics. The process that we use. So with biophysics, the interaction of biophysics, we can have techniques that image on multiple scales. We can make microscopies that go down to the molecular level, to the DNA level, or we can have techniques such as basically a camera, wide field camera, that measures, characterizes as organ scale, not organs as well. So the scales we can probe is it is safe. It uses non-ionizing radiation. This also means that it can, the techniques can be used at home, for example. It is miniaturizable, meaning that you can really squeeze down the size of these techniques into small microscopes, wearable devices. And most of all, it is relatively cheap. You want to buy an MRI machine from Philips that will set back a couple of millions if you want to buy a fancy microscope that will set through back something in the cross-sectional car. Much more I'll tell you a little bit before we start with all these theory and all these extractions. I will tell you a little bit about my personal background. I'm working in the academic medical center, I should say, then the first medical centers on the other side of town, in 18. And I have been working on a technique called optical coherence tomography for about 20 years. For those of you who do not know those key, I guess some of you have for a little bit. It's kind of the optical analog or the optical equivalent of ultrasound. So left hand side, you see familiar ultrasonic image of a baby, and then on the thing on the right hand side, spinning is an OCT image, kind of the same thing. The volume that shows you reflectivity as a function of depth, of position. The only difference is that the scale is much. The whole road that you use there is in size approximately equal to the location on the head. So it's really zoomed in. What you see in that skin image here is a piece of skin, and that little spiral over that little spiral over there is threaded. Yeah. OCT is an so it's been around for about a little more than 20 years. It's already being developed when I started. And it's a key diagnostic method of ophthalmology. If you go to the ophthalmologist with pain, there's a very big chance of listing academic hospital that they will make a OCT image. So you see the cross-sectional depiction of the eye there on the left, and in the green box, which is to see is a section of the retina, the netflise, where the nerves go out towards that same part is visualized in the middle image, cross-sectional image. We're looking in depth. These colors indicate the different reflection lines. And on the right-hand side, you see the picture what the ophthalmologist would take if he did not have, if OCT was not available, and they would just be able to make a photograph of the back of the retina, the right image. Now with OCT, you can actually look in depth. You can actually look at the conditions of these layers. So that seems to be about of these layers. And that was really a revolution in so there it is in the studies. There are two progress has not stood still. So here on the left-hand side is a zoomed-in part of such an OCT image that looks at blood vessels in the retina, so blood vessels. And the resolution these days is so good that if you look in between these blood vessels and blood cells, these are the rods and cones. So you can visualize the individual rods and cones. You can also track them, that you can come back a couple of weeks later after treatment, find that same set of rods and cones and see the treatment. Yeah.
I have a question because this technique, the OCT is mainly used in the treatment of eye diseases. Is this because it requires transparent tissue, or does it also work in opaque tissue?
It also works in opaque tissue, and I'll show you some examples in a moment. The reason why it is so strong in ophthalmology is really because it was the first time that it was possible to look in the retina, and look beyond the visual surface, where actually all these diseases take place.
The living eye.
Yeah, it's living eye. Well, that's some other progress, basically just technology, better computers, better cameras, better lenses, better light sources, etc., etc. So then the definitions, the pixel basically ranges, has increased over time. And it makes difference. However, if you look a little bit closer, then what the ophthalmologist sees is a pretty nice processed image. What the machine actually measures is the data on the right hand side. Fluctuations. Can you guess what these fluctuations are? Constant.
Noise, perhaps?
No.
Movement.
Yeah, movement. And what would cause this movement? So imagine sitting the patient still in the machine. The machine is looking no contact. It's still looking in the eye. It records. The machine stands still. The patient tries to sit still as good as possible. And still, this is what's hard. Yeah, it's the heartbeat. Because of the heartbeat, the eye pulsates a little bit, and that's what you see. And then, of course, the software is clever enough to know that, so it seals these images out before it's presented to the photo. The heartbeat is in there. So one of our PhD students, Roy, quite a long time ago, thought, okay, maybe we can use this information. Maybe we can extract the heartbeat from that. Well, the heartbeat itself is not so interesting, but he tried to correlate it to the blood pressure, which is a little bit more important. So then from this OCT data, he derived this pulsating pattern that corresponds to the pulse that you saw in the image. And then the red curve on below there is a control measurement. So it's the blood pressure. If you analyze these oscillations by taking the Fourier transform, with the spectrum, and in the spectrum you get peaks at the frequencies that are present in the signal. You can see nicely that there are frequencies that are fundamental frequencies of 1 Hertz, and then some higher order harmonics at 2, 3, 4, etc. Both in the OCT data and in the controls. So it's more than just an image. There is more data in there. Now I know that this example is a little bit overwhelming because every one of you now has a device like this on their wrist who can do it. So it's not so spectacular anymore as it once was. But the idea that there is more information than just the image, that is basically what our group is trying to do. So try to make images, but we also try to extract more data. Now. Back to your question, can we do that OCT in other organs as well? Yes, we can. This is what you see here is an OCT procedure performed in the urethra. The urethra is what connects the kidney to the bladder. It's a very small organ, very thin wall, and there's really no good way of visualizing that wall with any other technique. So patients, cancer patients with tumors developing in the urethral wall, basically the diagnosis was difficult. There was some suspicion that there might be something going on, that only an operation and taking out tissue could definitely say that was the case. So our hypothesis was then, okay, can we go in with an OCT scanner and make images and see if we can find any problems there. So you saw in the movie. So what you see here in the movie is the endoscope going in. So that is the endoscope itself is a little bit bigger. It has a camera, a white light camera on the tips, and the doctor could actually see what it's doing. The OCT probe itself is a little bit like a lighthouse. There's a light beam that rotates around a central axis, and the reflected light is recorded in the same way, so into the lighthouse. And then, while rotating, the focus slowly pulls back, so it takes this makes this helical pattern where it scans the data and then builds up. those are these images. Well, these images are then rendered, of course. So this is like a 3D rendering of a segment of the tube, and the locations that are marked in green represents small tumor. So this then allows you to to visualize and to localize this tumor, to measure how big it is, for example. Try to assess how deep it has grown into the wall of the root, etc. So that gives valuable information in how to proceed in treatment. We made a small study of that. So we included a couple of patients and tried to visualize differences between different stages of the tumor. Stages. The stage of the tumor is the amount of which it has grown into tissue. So that's something about growth. And then the second parameter that characterizes the tumor is the grade or the aggressiveness. So you can have a tumor which has an advanced state, so it's big, with a very low grade, which means that it's not very active. That's kind of range. I think that in the circumstances, if you have a small tumor that's very aggressive, then a different treatment. So what we have been trying to do here is through staging is based on illusions, so trying to locate the tumor on the image and see how big it has grown. And then the gradient, the aggressiveness, we hypothesized that we could assess that by measuring other data from the images. So just like with the eye, extra information here. We quantified the scattering properties to see if we could distinguish between low grade and high grade tumors. Well, the result is then over there. It's a small difference. It's not too big in this case, but there is indeed a difference. This is another example. I won't go into too much detail about that. It basically does the same thing. We can have prostate tissue. So here too, we can make all these images and correlate these images to how the tissue looks like on the microscope. After the procedure, the tissue is taken out, it is colored, and then the pathologist looks at the microscope, and you can compare. And likewise, you can calculate the properties again and see if that correlates with that's what so what's then basically the trajectory of OCT, because that is the technique I've been talking about for the last 10 years. So I started out time domain, which is a term that you will hear more about later from Johannes, but it basically means that it's very slow. And in applications only ophthalmology. So that's how it started. Then after that, there was a jump in technology, spectral domain, which is actually much faster. And then a new application field called popular cardiology. So it is still used there today as well. And then now, more or less, we're in the somewhere in the phase between OCT 2.0 and OCT 3.0, where we can increase the speed or increase the resolution, so it gets better and better and better as we go along, and we can measure more and more parameters, flow and diffusion and this kind of things. So it's still continuously in development. I guess the endpoints for that would be hopefully would be some kind of optical biopsy, so where you do not have to take out the tissue and examine it, but you can really do that examination in the patient itself. Okay, then the question is, so I showed you this graph where there was a difference between high grade, so aggressive, and low grade, less aggressive. The next question is, where does this contrast come from? That is a question that goes towards tissue. So we know what happens with the cells that progress from normal to cancerous, is that there are certain changes, certain morphological changes, functional changes inside the cell. So normal cells which have large cytoplasms, that's cancerous cells, they shrink a little bit, small cytoplasms. normal cell only has a single nucleus, whereas a cancer cell can have multiple nuclei. And that goes for other organelles as well. The reason for this basically is that the cancer cell is really impatient. It wants to divide, it wants to spread, it wants to progress. So it basically pays very little attention to its proper growth. So that it gets kind of messy. So these changes do occur. And what we observe is that normal cells, these regular, well-behaving cells, scatter light only very weakly. Into cancer cells, we observe stronger scattering. So that's there's little asterisks over there because it's not always the case. That's a little experience, but in general, this would be the trend. We did some experiments in the past to validate, basically prove the hypothesis. We did that by putting cells, so we just in a petri dish, let them go over apoptosis. Apoptosis is protein cell death, so what happens as you continuously refresh your cells, the old ones die out and you refresh cells. Again, apoptosis is the mechanism by which cells but if they die, the same kind of morphological changes depicted in the cartoon there on the left. So you start out with a healthy cell, and as it goes into apoptosis, it falls apart in different fragments that are then cleared. So as a function of time, you can reduce that apoptosis, and we did that. We did a couple of measurements. We did OCT measurements measuring the properties. That would be the black line in top graph. There was also a control group where the cells did not have apoptosis at all. We were in the same conditions. We were measuring something else. And there you can actually see this change. I'm not going to say it's an increase or decrease, but you see this change in properties. Just finish the sentence. And a second technique is by looking at fluorescence of these cells. And there also you can see that there was an increase in fluorescence in the photonic group. So basically, it showed us the demonstration that the hypothesis is correct, or the hypothesis is reasonable that if these changes occur inside cells, you can pick them up with the next condition. Yes.
What does the property on the y-axis mean in the above picture?
It's attenuation. Attenuation is vervanging. So it basically tells you how fast the light decreases in intensity as it goes along. Units per millimeter. So think of it really as if you would put a beam of light into a medium. If it would very slowly decrease in intensity, you have low attenuation coefficient, it would drop off very fast. So then the research questions in our group basically said, okay, how can we use this? How can we use this mechanism? How does it work? How do changes in tissue functionality and morphology during disease progression? How do they translate into these changes of optical properties? Do we understand the biology? Do we understand the mechanisms? Then the second question is, can we measure the properties quantitatively as a result of these changes? And if we can we then translate our optical properties into a meaningful diagnostic? And summarize, the problem here is summarized a little bit in that cartoon about the dragon and tracks. So the first question is, if you have a dragon and you observe that it leaves some tracks, if you know what the dragon is, you can predict what the tracks are going to. But on the other hand, if you can only measure the tracks, then you need a pretty good description of the dragon in order to be able to say, okay, this is a dragon, or it was just a passing dog. So that kind of summarizes the problem that we're facing, and it also shows you the importance of this modeling. So trying to understand how the light, how the competition behaves, and how the changes the structure. All right. So then a little bit of a bigger picture. We're not the only group that works on these kind of problems. In the Netherlands, there's a couple of electronics research groups at the technical universities. And in Amsterdam, as you can see, the Amsterdam position is pretty strong with IFA 2, the Amsterdam University Medical Centers and the Atomic Programs. We have basically strong position. Okay, so what can be then role of bioelectronics in this shift in health? In terms of policy goals, we want better clinical care, so more efficient clinical care is, I guess, what we mean. Means shifting to minimally invasive interventions. So you can prevent big operation and do that by surgical types of surgery and recovery time for patients is much less, and the burden for patients is less. It's good for patients, but also for costs because they will go. There is a shift to care at home, so there's a shift to prevention. And also very intriguing policy goal is a personalized medicine. So not one big treatment that fits all patients, but will work on average, but really trying to make a personalized diagnosis of the patient and tailor the treatment. At the same time, so I argued a little bit in the first two slides that there was a role in that whole transition. At the same time, we see that at present, the clinical acceptance of really good use of bioelectronics is not yet as great as it could be. If you look at the numbers for Europe and the image guided minimally invasive interventions, so actually the first bullet point of the goals, bioelectronics is only used to 5% of the cases. 5% of the cases very that could have been. There is still room for improvement. The reasons for that is that there were some big surveys that has been reasons for that. Well, it turns out that doctors find it difficult to use and to interpret. Use something that I think is solvable with better machines and using interfaces. But the interpretation of data is challenging. So you either have to make a better presentation of the data, or you have to train what is working and what we will see. A big problem is lack of codification and lack of standardization, meaning that if you buy one machine and one vendor, it will give you some data of some numbers, and if you buy the same machine from another vendor, it can give you different numbers. So that is, of course, not desirable. Inherently, with optical techniques, you cannot use NV, so MRI and CT can measure, you can more or less whole body images. With optical techniques, you cannot. Difficult to use and to interpret means that basically there are experts in the field who can do it, so there's a high expertise and dependence. And the last but not least is we can measure everything, but not everything is useful information. So we have to. We need to be able to filter out what is useful. So these are a couple of the challenges that we have in the field, and they will certainly come back every now and then. Discuss them. All right, that was my introduction. So let's have a break. 10 minutes, no? So the toolbox that we will have is basically physics and mathematics. And within that toolbox, we have two theories. We have semi-classical theory, where light is treated classically as a wave, but the material is treated by methods of quantum mechanics. Even though usually even the classical treatment of material will just fine. And then we have this quantum electromagnetics, where both the light and matter get full quantum treatment, which basically means that if you use this one, then you would be able to treat all optical phenomena. They can all be explained, including those that are described by semi-classical theories, or including those that appear to describe wave-like properties. Going away. Much better. However, whichever of these theories we may choose, we are obviously interested in observables, in the output of experiments. So basically, whatever is under the surface, be it quantum theory, be it classical theory, being whatever we calculate, what we are interested in is observables. And in the semi-classical treatment, that observable is power, optical power, watts, or maybe it's power flux, so watt per square meter, or maybe it's power density, watt per unit volume, but it's power. That is what the observable is. And in this quantum treatment, the observable, or the outcome, is a probability, the probability of something happening. So that could also be the probability flux, so the probability of something happening per unit area, or the probability of something happening per unit volume. It's a little bit mind-boggling, but these are the things that we're ultimately interested in. So whatever these two means. So what I want to do now is take a little bit closer dive into how both of these theories work, and then compare them in the end. So let's start with this quantum electrodynamics. Paraphrasing Richard Feynman, it describes the intricate dance between photons and electrons. Feynman was a little bit of a poet, so he kind of gave a very difficult theory a nice cultural spin. The dance of photons and electrons. You see the word photon there. The word photon already can make a grown-up people cry. This is Helen Bicknell, professor of quantum optics, no less at MIT. And he says if you give the photon too much reality, you get into trouble. That's not really encouraging. And Einstein, Einstein. What are light quanta? Everybody thinks he knows, but they're deluding themselves. So there is a little bit of reason. So what is a photon? A photon is a particle, and we call it a particle because it is indivisible. And a photon either shows up or it doesn't. That's what the indivisible part means. There is no such thing as half a photon. And there is an experiment to show that. So let's say we take a very, very, very weak light source, a light source that only emits one photon at a time. So we direct that light source at an instrument called a photomultiplier, so a detector, which works as follows. The photon is incident on the photocathode and makes free electron in the photocathode. That electron is accelerated in an electric field towards different diodes, which have different voltages, so that at each dynode, more electrons are created. So in the end, you get a whole avalanche of electrons at the end of this instrument, and all these electrons together, that large amount of electrons give you a measurable current. So every single photon through this photomultiplier is converted into something that you can measure with your full method. So that weak light source emits one photon at a time. So if we do this experiment in time, what we would see every now and then is a pulse that arrives when a photon hits that detector, and then after some time another pulse, and then at some other time another pulse, and another one, and another one. A couple of things: these pulses are all of equal height because all these photons are identical. They give the same response, so you get the same pulse height for each photon. They will come irregularly at time. You never know when the light source is going to emit one. So basically, this shows you the particle nature of photons. Incidentally, it's very funny thing to realize that if our retinas would be, I think it was 100 times, but maybe it's 1,000 times, but if it was, let's say, 100 times more sensitive, we would be able to see these individual photons. So then if you would then sit in a room with such a weak light source, you would actually see these little flashes on your retina. But I guess it's better that they're not, because that would be kind of distracting. Was there a question?
No, it's just straight.
Yeah, very good. So a photon is a particle because it's indivisible. It shows up or it doesn't. And then light, so in that sense, light is not a wave in the quantum theories. In the quantum theories, we only have fields. In fields, classic theories, we also have fields. A field is something that assigns a quantity as a function of space and time. So it could be, for example, the strength of your cell phone. You have a certain strength at a certain place in a certain time, and the function, the mathematical function that describes that is your phone signal strength field. The electromagnetic field, the classic electromagnetic field, is also a field. It's a so-called rapidly oscillating vector field. So the quantity that it describes is a vector, and that vector does not stand still. It oscillates in time. With that electric field vector, magnetic field vector, you can, for example, calculate the force that a moving charged particle experiences. That is the purpose, so to say, of a field. That's the classic field. Quantum field is a little bit different. It also assigns something in space and in time, but it assigns likelihood. So how likely or how probable it is to find a particle, in this case a photon, at a certain place at a certain time. So that's the quantum field in this case. That quantum field takes this form in complex notation. Assume that you're familiar with this complex notation. So it has an amplitude, the magnitude, and a phase term. The quantity, this quantity that the quantum field describes, is called an amplitude for an event. So there is a certain amplitude, this correct complex number, for let's say detecting a photon, or finding a photon at a certain place at a certain time. And if we now take the complex square of that number, of that amplitude, so we multiply it with its complex conjugate, and you end up with magnitude squared. This magnitude squared is exactly the probability, so just an observable probability between 0 and 1 of detecting a photon at a certain place and at a certain time. That is what is calculated. So in the basically in the quantum theories, we can only calculate probabilities. You don't calculate absolute things. There is only a probability that you will find something. Of course, you all know the famous example of Schrödinger's cat, which is well, if you misinterpret it a little bit, people say it's dead and alive at the same time. No, it's not. It just has a certain probability of being alive. It has a certain probability of being dead. And once you open the box, you'll find out what it is. It's either dead or alive. So probabilities. Okay, so we calculate the probability. So I'll blow your mind a little bit further and then we'll stop. So these particles, these of the probabilities that we calculate are the quanta of the electric field. So the photon is the quantum of the electric field energy. The energy of the photon is Planck's constant times the frequency. It comes in these steps. This frequency is given by c over lambda, c being the speed of light in vacuum, with that, and lambda being the wavelength, the color of the light. So that's the energy. And then behind my zoom thingy here, let's put this here. Just to have all complete, if you multiply the frequency here with 2 pi, you get the angular frequency. That is given by 2 pi times c over lambda. And if you combine 2 pi over lambda into 1 new number k, that's called the wave number. Basically, also describes the color. So the photon is the quantum of the object. If the so-called quantum state of the considered system, which is a very complicated way of saying just what the amount of light that we're studying. If that has many photons in it, then basically we have a strong light source, and a lot of photons spread at the same time. And if that is the case, then the semi-classical theory works pretty well. We do not need to resort into all these quantum probability theories. Although even at low, but if you're working with very low energy, we have only one or few photons at a time, then the full quantum treatment is necessary. So we will not go into a lot of details of this quantum theory, but there are some concepts that derive from that, and some rules and some principles that are very useful to use anyway. Even though we're not working in the quantum limit, we can use some of the rules. So let's look a little bit closer into that. So we had this amplitude for an event, a complex number, and if we calculated the square of that, we ended up with the probability of something happening. If we the rule that is associated with these amplitudes is that we can calculate the probability for a certain event by adding together the contribution, what is then again with a very complicated statement, all possible paths in configuration space. Ignore the term. It just means that if an event can happen in a few distinct ways, then you have to take them all into account. So you have to keep all possible ways an event can happen into account. If my event that I'm interested in is photon traveling from here to here, then it can travel in a straight line. That's one way. It can also travel in a wavy line. That's also one way. Both of these ways are associated with an amplitude. And if I want to describe this whole system, then I have to take both of these amplitudes into account. This wavy part for a photon traveling from here to here might seem a little bit absurd. But in the quantum world, nothing is absurd. So it might happen. There is an amplitude for it to happen. And if you want to calculate the true probability of a photon going from here to here, you also have to take into account all these weirdness. That is the main contribution of Feynman to this field. He famously said that the rules are very simple. Only the way you have to apply them is it's like checkers or chess. The rules are pretty simple. But playing a chess game and playing a checkers game can be very difficult. Same thing goes on here a little bit. Being complicated as it is, Feynman was really good at visualizing how these amplitudes work. His way of visualizing it is this amplitude as an arrow, as the hand of a clock, so that it turns. As a photon moves from A to B, the hand of the clock starts turning. Each wavelength, each photon has its own speed. So that means that if you would have two photons simultaneously of different colors, and the stopwatch hand of the of the blue clock would turn faster than the one of the red photon. And the whole sequence, for example, of light being emitted by the light source bouncing some surface here at B and then going to the detector over there is described by following the movement of that stopwatch. And so what happens here? If the photon moves from A to B, that's an unobstructed move, nothing really happens, so just the hand of the stopwatch turns. Then at B, it is reflected. The rule for that, so the point is not to explain where this rule comes from, but the rule for that is that the hand of the clock shrinks a little bit, as it gets here, and it makes an opposite turn of 180 degrees. And then it continues running, turning until it reaches the detector. So you start out with a stopwatch hand that is like this, it turns, turn, then it shrinks a little bit, turns 180 degrees, and then turns a little bit further. You end up with the final position of that error. So the path in red was nicely symmetrical, but another way of getting there would also be possible, depicted here in yellow. So the light would hit the surface at a slightly different position and would travel to the detector. But the things happening are basically the same. So on the first step, it's actually a little bit shorter turn because the path is a little bit shorter, so it's a shorter turn over here. Then it hits, again, it shrinks. The hand of the clock shrinks, it turns 180 degrees. And then there's a little bit longer turn compared to the red situation when it moves to the detector. Yeah.
So in the orange case, both the A path and the C path result in a longer turn than the.
No, that's a typo. So the A path is a shorter turn.
Okay,
Yeah, I'm sorry. Yeah, so that's a shorter turn because the path is a little bit shorter, and the other one is a longer turn because the path is a little bit longer. And then if we take an even, so the same typo there. If we take let's say this path, so hitting the mirror here, then there's an even shorter turn going here. Then again this shrink, turn 180 degrees, and then an even longer turn going to the detector. Now each, yeah.
What determines when you have a shrink and a turn or without?
Yeah, this is simplification, of course. If you go a little bit further into what actually happens, then then what you would need to do is, so this is not a different thing, it would be a mirror, but that mirror would be composed of different layers, the photon could hit exactly at the surface, but it could also hit a little bit below the surface, like a layer there. And all these things all have the different arrows and different strings, and which would all have to add all together, but the net result is this.
Okay.
That's why it's there.
Just what we're talking about time since the stopwatch, or
Yeah, basically it is time. So as it moves along, the arrow just turns, and if it takes a shorter path, then the turn is short, and if it takes a longer path, the turning is long. So in this case, you get three different density expressions, where the length of the arrow is all at the same time, but the turning is different. So they all end up at different angles, because the sizes of the arrows of the stopwatch hands in this case. So if you would calculate now the probability of either of these paths, you would have to square that. So square this 0.2, and you would end up with a probability of 4%. So regardless of whether the path is goes from here to here or from there to there, the probability of that path is 4%. But the rule says we have to take into account, so this is all each probability, but we have to take into account all of these probabilities. So we take then the stopwatch hand. So So A has a net turn, so it started out here, and then it turned, it shifted 180 degrees, and then it turned a little bit more. So let's say that A ended here, stopwatch end. The one from B turned a little bit further, so it ends up under this angle, and C to a little bit further, so it ends up here. We have to add all these probabilities together, so you stack these arrows in a row, and then the final length is this. And then the final event of the final probability of a photon going from there to there, if these were the only three possible paths, would be the length of this. So for each of the individual trajectories, it could be 4%. But now, because you have to add them all together, it can be something else. And what it is depends on the turns that were made. Yeah.
So in the bottom case, we insert the final arrow. Are the A's in the bottom case the same as the ABC? Are they the same as the ABC in the top, or does each of those arrows represent a different path that the photon can take? So
yeah, so each arrow represents a different path. So the path in the red, orange, and yellow.
Yeah.
So this is red, orange, yellow, let's say.
Okay. So it's not the A.
No, sorry. No.
You should use 1, 2.
Yeah, I should. Absolutely right. It's a new slide, so it has not been field tested yet. So thank you. Okay, so that is basically the way these complicated things should be made up. So what we were doing here is so the stopwatch hand is of course really a factor that turns. If you add these hands together, you're adding factors together. So we're actually constructing factors in a complex plane, and there are rules associated with that that we can supply. These rules are the same rules that would apply if you would calculate just ordinary probabilities, meaning that if you have an event that can be cut into different sub-events, you're allowed to multiply the probabilities. If it can happen in multiple ways, you're allowed to have probabilities. And these rules are, these concepts are essentially the same. These arrows can have random directions, so you're adding random arrows, but there's also a lot of theory associated with that, so you could use that as well. And finally, and this is maybe the most important point, there is this, you can already see it in the notation, there's a resemblance between this complex notation of these arrows and that of the electric field with classical electromagnetism. So in this quantum field, you have this probability amplitude. In the semi-classical theory, you have the electric field amplitude. You can square both. If you square the probability amplitude, you get the observable probability. If you square the electric field amplitude, you get the observable power. So there is this connection between the two. So the hand waving part that we can okay, so if we are allowed to use classical theory because we have a lot of photons, we can actually use that to calculate probabilities of detection and vice versa. Final, I have to be careful. I want to share a lot of things here, but with a little bit of the risk of confusing you. This one is really fun. Because this essentially explains why light seems to travel in straight lines. So in the top picture, you have a source there, S. There's a detector that is positioned at P over there. So the source emits light and the detector obviously catches it. But in between is a block Q that prevents light from going directly to from the source to the detector. So straight line is not possible. And then on the bottom there is a mirror, and that mirror is divided into different sections. I remember 8 to 10. And just for simplicity's sake, let's assume that these are all the ways that the light can take to get from the source to the detector. Now, for each of these ways, these trajectories, you could draw an arrow, and in the end, to calculate the total amplitude for light going from S to P, you would have to add up all these little arrows. So here you see the time it takes for the light to go from S to P as a function of the segment. So the shortest time it takes is if it goes from S to segment G and then to P, that's the shortest time. And if it travels through the edges of the mirror, it takes the longest. So this is the time it takes. It also means that this will represent the angle that the arrow has made. So this longer time will correspond to larger angles, larger turns of the arrow, and the shortest time will correspond to a short. Now, if you add, and these the little arrows here are shown over here. If you would now add these and construct a final arrow, you will get something like this. So in the beginning, all these arrows have different turns, and you just add them head to tail, but nothing really happens. It just moves around here. And then as we go to the center of the mirror, all these arrows start to be aligning because all these paths are nearly of the same length. So here, all these arrows start aligning, and then if you go back to the, if you go further to the other end of the mirror, there the paths are really long, and it does not help much if you change from one position to the other. So the final arrow here, drawn then here, is almost more or less aligned with the arrows in the middle. So that means that the most important contribution to the light going from A to B are the paths that go through the middle. So even though it is possible for the light to travel through the strange paths at the edges of the mirror, they don't contribute much. So the light appears to travel as a straight line from S to G to B. One interesting question, one interesting thing to think about is what would happen if you would, now let's say you would block every second segment in this mirror. What do you think would happen? It's not intuitively very clear, but what would happen is that this turning around of these arrows here, because they all have opposite lengths, if you would very systematically take out a few segments here, then this going around would not be possible anymore, and you would get the final arrow, for example, that points in a direction like this. So you would get so the light would start. It would seem to appear that the light does not travel in a straight line anymore. You can actually make such a thing. It's called a diffraction grating. Okay. Let's go back to a little bit more familiar ground and the observable in the classic theory, the intensity. So the first slide had Maxwell on slides famous for Maxwell's equations. Here they are differential equations, coupled differential equations that relate the electric field strength and the magnetic field. So these are the fields. There is material properties in here, epsilon, the permittivity, and mu, the permeability, the associated units that describe the material. The symbols over there, the nabla is a shorthand symbol for differentiation with respect to space. If you take the inner product of this operator with the field, you can so-called divergence. You can take the outer product, that would be curl, and you may be sure to recopy that and refer you to this wiki page. The set of equations can be solved, or can be combined into a single second-order differential equation for, let's say, for the electric field. So on the left-hand side of that equation is differentiation, double differentiation with respect to spatial coordinates. On the right-hand side is twice differentiation with respect to time, and these material properties are again in there. You can solve this equation by standard techniques, and then one of the simplest standard technique is to try putting in sine and cosine functions. This will travel in space and time, so you can fill that in and see what the constants that you put in front should be. And this works. In this case, this works perfectly. So the parameters in this solution are then the wave number, the one that you saw a little bit earlier on. So, K is 2 pi of the lambda the wavelength, and the propagation velocity. This expression in cosines and sines means that it has amplitudes and phases. So the phases is in between bracket here. So that also means that we can write this solution of sines and cosines in the complex notation that we saw earlier. As an amplitude complex exponential interface. And rearrange a little bit within the phase term and with this expression for traveling now. Fill it in and do some manipulations, and it turns out that omega divided by k, so the frequency divided by the wave number equals the velocity of the wave. So we started out with, and that is completely expressed in terms of material properties. So the velocity of that wave is given by the properties of the material. By the permittivity and permeability. We can split these properties, epsilon and mu, we can split them into values for vacuum, here in red, and relative, so-called relative values that this is the multiplicator, which is typical of the material. So then epsilon null and mu null are values for vacuum. Which means we can rearrange the top equation a little bit, and we can write the velocity of the wave in terms of vacuum value and in terms of the factor that depends on the material properties. This vacuum value is the speed of light in vacuum, c, 3 times 10 to the power 8 meters per second. M, the factor correcting for it, the factor that is dependent on the relative material properties, is called the refractive index. So the refractive index is the property that scales the velocity of light from vacuum to a medium. Refractive index. Just a note: this refractive index is not a constant. So c, speed of light, is a universal constant, but the refractive index is not. It depends on the material properties. So it is different for every material, but it also changes with wavelength. So it can have a certain value for red light, and it can have other values for let's say blue light. So it's not just a constant. Okay, then the solution of Maxwell's equations that gives you an electric field and a magnetic field. These fields are both in phase, and they both oscillate perpendicularly to the direction in which the wave is traveling. So here the wave travels along the x-axis. That is travels along the x-axis. The electric field also oscillates along the y-axis, and the magnetic field oscillates along the z-axis. The direction of propagation is denoted by the factor k, the wave factor k. And we can write it as the outer product of the electric field and the magnetic field. Maybe you remember this Kirk-Dreyer-regel, this rule that if you have the outer product of two factors, then you I don't know how it works. You make a turn and then you get the direction that is perpendicular to both. This magnetic wave factor, so that gives you the direction of the field. It has magnitude, that is again the superior wave number. That relates. So that is related to the current. So now we're finally getting to the observable. The energy that is contained in this field then flows into the direction of k, and it is represented by the so-called pointing factor. The definition of the pointing factor is given here. Because this field oscillates very rapidly, so does this pointing factor, and it has contributions from the electric field and from the magnetic field. Now, because it oscillates so rapidly, no detector that we can devise can actually measure that oscillation. So what you measure in an experiment is an averaged version of that pointing factor. So it's average. Allows us to simplify this equation a little bit. It has has a given direction. So the direction S here is aligned along the direction of propagation. So it is aligned in K units. Look at units. This expression on watts per square per area. Watts per square meter. So, in summary, we have, starting from Maxwell's equations, we can calculate the electric field and magnetic field. They both contain energy, and the flow of energy, the direction of flow of energy is given by the Poynting field. The Poynting factor, so that is what you measure is then the time average version of that. That's the second equation over there. But luckily, the amplitudes of E and B are proportional, so we can express this completely in terms of the electric field alone. So we can define the intensity here as the product, complex notation of the product with the complex conjugate of the electric field and get the intensity. And then we have some notational variants over here. Let's say simply we'll say that the intensity, which you can measure, is the square of the electric field. So either with complex notation or with some average brackets around it. It is all the same thing. What we measure is the test. To give you a little bit of feeling for how these numbers work. So if you have the intensity of sunlight on a bright day on the surface of the Earth, that is about 1 kilowatt per square meter, and the intensity of moonlight, much weaker, is about 2 milliwatt per square meter. Just for fun. Okay. Fine. Yeah. So you notice that we get a couple of state manipulations in the quantum approach. We calculated an amplitude for an event to happen, and then we squared that in order to get the probability. Here in the semi-classical approach, we calculated an electric field, and we squared that to get the intensity, to get the measurable, observable quantity. So let's say we have this experiment with cuvette, and we shine light through that. It's a weak light source, and the photomultiplier is there against it. It's only one photon at a time, and the photomultiplier detects these photons. Now in the cuvette, there's an absorbing substance, so some of the light will be captured by that substance. And let's say that one out of every photon makes it. One of every photon that is generated by the light source makes it to the detector. Yeah.
You mean 1 out of every 100?
On average. Okay. So not every time 99 and then it goes. On average, 1 out of 3. So that means that 99 out of these 100 photons get absorbed in the qubit. Okay, now we let this experiment run for a long time. So what do you think? What is then the average detection probability?
1%.
Yeah, 1%. Yeah. On average, 1 out of 100. So that's what you look at. Yeah. What? So now in the lab. You can, let's say you measure the intensity of the light source before the qubit, and you measure the intensity of the light source behind the qubit. What can we expect then for the ratio of E behind the qubit and on the 0 before the qubit?
Also,
yeah, also 1%. That's the same thing. You can make it formally if there's n photons emitted in the time t, then the emission rate is n divided by t. Each photon has because it's a quantum has an energy of h times v in joule. That means that the emitted power will be given by n times h times the frequency. The detection rate is 1%, so you can do the same calculation for the detected power and then calculate the ratio. Well, what you thought intuitively is of course correct. It is 1% as well. So this. So again, this is then this link between the detection probability and what you would actually measure if you did the experiment. On average, this should be the same thing. So one side step, if the average detection probability of is 1%, what's then the amplitude detection?
Compared to what?
So so we had in 1% we had the amplitude for an event, and we had the probability for an event. So if the probability is 1%, what would then be?
Function multiplier, which is
Yeah, but what is the number?
Be the square root of 100, so it would be 1/10.
Yeah,
right?
exactly. It's that the amplitude, and the probability was the amplitude compared multiplied with its complex conjugate. So the magnitude of this amplitude we would want, of course, the phase we wouldn't know because that's. So summary. In the semi-classical theory, the observable is the intensity. We calculate that from the electric field. So the electric field here is here in complex notation. This is basically just the wave description of light. We encountered all these parameters, all these quantities to describe this wave. We have the wave vector k, which describes the direction, the wave number, which is related to the wavelength to the color. So k is 2 pi over lambda, and there's a frequency in there, and that was if you have material. There's a refractive index in there that tells you how much the speed of the wave is reduced compared to vacuum if it travels in the medium. And then on the other hand, for the quantum field theory, we have probabilities as the observable. These were calculated from the complex square of the amplitudes. So the amplitudes are here in complex notation, just like the electric field. And along with it can be set of rules, which we briefly touched upon. But conceptually, we have this link between intensity and event probability, so the observables, and then underneath the multicup, when we calculate it, we have this link between electric field and the amplitude of the field. Okay, exactly now. So let's take a break again. 10 minutes still sufficient? Yeah, okay. Okay, let's continue, people. So the main interactions of light with tissue, absorption is scattering. So absorption is really the loss of light, and scattering is the redirection of light. So the classic experiment with which to study absorption, and also the experiment I'll refer to quite a lot in the lecture is, so let's take a cuvette, shine the light, measure the intensity of the power before it enters the cuvette, measure the intensity of the power after the cuvette, and then try to infer what has been going on. So in the lab it would look like that. The experimental drawing is over there. So if that light would be a laser beam, for example, if the cuvette was filled with water, you would put a screen on the other end, which is the red laser, the laser spot. In this case, the red laser spot. Now, if we add absorbing material into that cuvette, into the water, a little bit of scattering material in order to direct light to the camera, and we take photographs of it. And what you will see if you increase the amount of absorption, you could clearly see that the distribution of the light inside the medium changes. So that is the first effect of adding absorption. You lose light, but also the overall distribution of the light in the tissue changes. So then the question is, what happens to this absorbed energy? We'll get into them. So the significance of absorption is given here. This is an overview of all the electromagnetic-based imaging modalities we have available. So on the left-hand side, we have the gamma rays and the X-ray imaging. On the right-hand side, on the long wave-hand side, there is microwave imaging, MRI imaging, and then in the middle of the spectrum is the niche for visible light, where optical imaging takes place. So most of us exist of water. 70% of us is water. So it is reasonable to assume that the absorption properties of water are the important properties that govern overall how this electromagnetic radiation is interacting with tissue. So if you now look at the absorption spectrum of water, in this case it is not on the wavelength axis but on the frequency axis. If you look to the absorption coefficient of water, then you see low absorption in the radio wave side, you see low absorption in the gamma ray side, the X-ray side, and we see a dip in the water absorption for the visible light. So if you plug in these imaging modalities, you can see that all these they all work in the regions of the electromagnetic spectrum where the absorption of water is low. And of course, it has to be low because otherwise it would all be absorbed and you would not detect anything. You could not do imaging. So the imaging works in the regions where the absorption of water is low. Yeah, so this is on frequency axis on the wavelength axis. Okay, we've encountered these already. Then if we look at imaging techniques that are currently being used in the field, so all are based on low, all are operating in regions where the water absorption is low, but still you can see some huge differences in the resolution which they have, so the small structures that can resolve and the depth of which they can move. So in the top right corner, we have again MRI and CT. PET and these techniques, so they have a huge imaging depth. They can look through basically through our bodies, but their resolution is pretty coarse, so in the order of millimeters. The optical techniques that work in this niche, on the other hand, have a resolution that is much better, so in the order of micrometers. But the depth with which you can image is much lower. A little bit too distracting. Right, so water is the most important absorber, but it's not the only absorber. Others include hemoglobin, that is the protein in your blood that carries the oxygen. So you have an oxygenated form and a deoxygenated form. And as you can see, as a function of wavelength, the absorption properties vary a little bit, and also you will see that absorption is pretty strong compared to that of water in the visible region. Just to quiz you a little bit, so in this graph, you know what the visible light region is approximately, which wavelengths? Yeah. So you have also fatty tissue absorbs melanin, the pigment in your skin that gives you skin color, is of course an absorber. Different proteins have different absorption spectra, etc., etc. So if you want to, if you ever need a good source for this absorption spectra, they'll compile at this website. So what happens to this energy, this absorbed energy? Well, it can be converted into heat. So if you direct a lot of light to tissue, you can heat it up low. You can do a calculation of that with an equation typically like this. So this would calculate the rise in temperature as a function of the amount of light you put in. So you see there on the very right is the fluence rate, as units watts per square meter. So that is the amount of optical power that you put in. The absorption properties of the tissue are in there, and there's some mechanical properties as well. So typically you would need to solve an equation like this in order to calculate the temperature distribution in the tissue according to So a technique that uses this heating is photoacoustic imaging. So what happens there is to shine a laser pulse on tissue. That light is absorbed, so the tissue heats up. Due to that heat, the tissue expands a little bit. That expansion generates an ultrasound wave, an acoustic wave, and that ultrasound wave can be detected on the outside with this ultrasound transducer, just like as with echography of the babies. So that technique is of course, because it is based on this absorption generates heat, generates ultrasound wave. It is very sensitive to local absorption in tissue. So, for example, in blood vessels, a lot of if the blood absorbs, if you use wavelengths where light is absorbed by blood a lot, you can get strong photoacoustic signals. That's a relatively new technology, but it has been developed. Basically like crazy over the last 10, 20 years. And the graph on the right-hand side actually shows you where people are now applying this photoacoustic method. The real benefit is that you can just very precisely measure the location of blood vessels. Location of blood vessels is important to know because, for example, around tumors, you have lots of blood vessels. The tumor wants to grow, so it actually stimulates the growth of blood vessels around it. And so if you can find regions in the tissue where it seems like blood vessels have proliferated stronger, then that can be an indication of the presence of a tumor, for example. This is just as an example of the kind of images that you get. You can play around a little bit with the color of the light that you use. You saw the absorption spectrum just now of oxygenated hemoglobin and deoxygenated hemoglobin. They're slightly different. So that means that you could expect a different response for blood that carries oxygen and blood that does not carry oxygen. So that is what you can see there on the left-hand side. As a function of the amount of oxygen in the blood, you get different responses. So not only could they map the vasculature, but they could also map the oxygen content in there. The picture on the right then shows the visualization of the vasculature around the tumor. One of the applications that our colleagues in Twente are using this is for mammography. So for as a kind of less burdenful way of making mammograms, and that is actually working quite well. So heat is one of the mechanisms that the absorbed energy can be lost, but the energy can also be converted back into a photon, converted back into light. And in order to describe these processes, I want to talk you to two diagrams. This one is called the Bmo Lti diagram. It gives you an overview of the electronic energy states in a molecule. So the molecule is the molecule that absorbs the light, and it gives you all the possible energy transitions that can happen in this molecule. So the thick lines, the thick blue lines, are the vibrational ground states. The thin lines just on top of that are the higher vibrational states. And the dashed line, which is not in this figure, it will be another one, is a so-called virtual energy state. So what can happen, for example, is that the molecule initially is in the ground state, and then it absorbs a photon. That is the excitation of the molecule by absorbing a photon that is given by the green arrow over there. So it gets excited into a higher vibration state. And from that, it can, for example, relax back to the ground state. If there is no radiation coming free from that relaxation, then it is converted into thermal energy. So that is something that you would, so that is the Bmo Lti diagram that would correspond to what happens in photoacoustics. Another way of looking at this absorption process is in so-called space-time diagram. So here we have space on the right hand, on the horizontal axis, and time going up on the vertical axis. That's a little bit different than we usually observe. And what you see in this space-time diagram is what is used in quantum electrodynamics to depict these processes. So this is a very simple one. It shows you the movement of particles. So it could be a photon moving from R1 at T1 in space to R2 T2 in space. It's the blue arrow, and then simultaneously there is a particle moving from R3 at T3 to R4 at T4. So just two arrows in this diagram. So in reality, this diagram corresponds to the whole complex quantum thing. So there is an equation associated with it. There is an amplitude associated with these processes, which you can square to calculate the probability, etc., etc. But for now, it is just for visualization purposes. Because in the quantum world, strange things can happen. Also, you could draw the orange arrow like in the bottom graph. That is a particle that moves from R4 to T1 to R3 and T3. So that is basically a particle that moves back in time. In the quantum world, everything is possible. So one of the mechanisms where radiation is generated after an absorption event is called fluorescence. So this is the Lti diagram then for fluorescence. So the molecule is initially in the ground state. It absorbs photons, so it gets excited, the green arrow into a higher vibrational state, and then there is some relaxation, radiation does with relaxation to the first excited ground state as well, for example. And then from that, it relaxes further to the ground state, and that relaxation is accompanied by the emission of a photon. That is then the solid so this is an energy diagram. That means that the photon that is emitted has a lower energy than the photon that was absorbed. And if you remember, the photon energy was E times Planck's constant times the frequency phi times the frequency. The frequency was C over lambda, so it is inversely proportional to the wavelength. So that means that the fluorescent photon has a lower energy than the incident photon. It has a higher wavelength than the incident photon. So that is the process of fluorescence. So what is now the purpose of this space-time diagram? So we can draw the space-time diagram for that same process here. So the molecule is stationary, so that is one big solid line in space. It does not move, so it's a straight line. Then the first it is in the molecule is in the ground state. Then the photon is absorbed, it is the green state, and then after some time, this transition, the transition that you saw in the previous diagram occurs. After some time, the photon is emitted. That is the red wave. What you could not see in the previous diagram, but what you can see here is that there is a time lag associated with it. So the molecule spends some time in this excited state before the new photon is emitted. And in the fluorescence process, that lag time can be in the order of picoseconds to microseconds. It can be reasonably long. Again, yeah.
It's always that the photon goes from the S0 singlet state to the S2 and then back to the S1 non-radiated and then to the 0 again. I thought it's mostly like going to the S1 and then on different vibrational modes and then back to the S0.
Yeah, but back to the S0 is where so that's just so this one you say this one you agree with, I guess. Yeah, it's a little bit so the states here are the molecular or the molecular state, so it goes to AS2 and excited S2 and then it relaxes back to the first excited ground state, so to say, and then it relaxes to the true ground state, and that is where the photon is.
Okay.
And that whole process takes some time, so this is in the order of picoseconds to microseconds. But what's Dylan? This out of the way. sorry about that. So again, this is a random process. So that means that there is not a single fluorescent time. There is just there's the random time it takes. A random time that the photon spends in the excited state, and then on average it is in the order of picoseconds to microseconds before it falls down. So if you would do a measurement, you would detect these fluorescent photons at different times, at different time distributions. So these are some pictures of how you can use fluorescence to label different compounds in tissue. So each of these compounds has different energy transitions, so it will have different fluorescent spectra. So by exciting them with a suitable wavelength and by detecting only light that corresponds to the fluorescence, you can very specifically see different molecules or different tissue types inside that. So that gives you these beautiful microscopic pictures like this. This fluorescence effect can, as described before, was only using one photon. So it was one photon that excited the molecule, and then there was a photon emitted. You could also use two photons simultaneously, with each with half the energy. But if they would absorb at the same time, they would still bring this molecule into the excited state. So it's depicted here in this diagram. So you have two photons exciting, and then again one photon emitting. That could be done for two photons. That could be done for multi-photons, for 3 or 4 or 5 photons. What do you think would be the advantage of doing such a complicated trick? Why would it be beneficial to have 2 photons rather than just one? That's true in a sense, because if you use photons, so now in this case the exciting photons have a smaller energy, which means they have a longer wavelength. And light of a longer wavelength in general penetrates a little bit deeper. So that's true. That is one of the
Easier to produce a lower energy.
Yeah, that's true. And what's also true is you can now have the situation where you can excite photons actually with a longer wavelength than the photons that are emitted. Instead of using only one photon. So there can be some experimental benefits. With Marloes Groot, we'll talk a lot about some multi-photon. So again, the timing is then more or less the same. There are 2 photons absorbed at the same time, but still there is a certain lifetime associated with this process. You can also measure this fluorescence as a function of time. Phosphorescence is very similar to fluorescence. It's only just a little bit more complicated. Here, the molecule has a triplet, has a set of triplet states as well, where after excitation, there can be some energy transfer to a triplet state, and then followed by a decay to a ground state from the triplet state. So the effect, so the experiment is not very different. The only thing is that if you look at the time diagram, you'll find that the lifetimes of phosphorescence are much longer than that of fluorescence. So phosphorescence can have lifetimes of milliseconds up until hours. So these glow-in-the-dark sticks, which you can break and then well, for some time, these are based on phosphorescence. So the process lasts much longer. So again, here this is a random process, so not a single lifetime, but the distribution of lifetimes. This effect has been exploited in order to measure oxygen tension in cells, and I'll explain it briefly how it goes. So the molecule involved is a so-called metalloporphyrin. You see the Jablonski diagram over there. So you have a ground state, absorbs a photon into the excited state. So normally, in terms of if you would have fluorescence, you would have this non-radiated decay back to S1, and then emission of a fluorescent photon back to S0. That would be prompt fluorescence. But now there is a triplet. Now this molecule has a triplet energy state as well, and there can be an energy coupling between the S1 state and the T1 state. So that means if there is energy transferred back and forth between S1 and T1, as long as this is happening, the photon is not emitted as a fluorescent photon. So there is also next to the prompt fluorescence that just goes this direct pathway, there is also delayed fluorescence that first has been involved in this intersystem processing and then goes back to the ground state. Also, you can have phosphorescence as well. So again, energy transfer to the triplet state and then decay to the ground state, phosphorescence. Now these processes all occur, but in the presence of oxygen, they are modified. Oxygen is a molecule that has a triplet ground state. So there is a very good coupling between the triplet state of this metallic porphyrin and the ground state of the energy state of oxygen. So it means that in the presence of oxygen, a lot of energy will just be transferred to the oxygen molecule and therefore not available for phosphorescence or for delayed fluorescence. So if you put this metallic porphyrin molecule in tissue, you can kind of use it as a probe for how much oxygen is available. If there's a lot of oxygen, you will see very little phosphorescence and delayed fluorescence. If there is not a lot of oxygen, you will see stronger signals for fluorescence. This has been done in vivo, so in kidney of the rat, if I'm correct. So what you see here is the Boltzmann diagram on the left. On the right-hand side, you see time traces of delayed fluorescence. In two cases, in the case where there is little oxygen present, so 1% oxygen in the environment, where you see a strong, longer-lasting fluorescence signal, delayed fluorescence signal. And when there is a lot of oxygen, that fluorescence signal is quenched. So this shows a smooth decay. You can associate the decay time with that curve. That is shown in panel D as the decay time as a function of oxygen pressure. So you can nicely see that the more oxygen is there, the higher that decay constant will be, so the stronger the oxygen is. And the stronger fluorescence is suppressed. So that was delayed fluorescence lifetime imaging. You can also do phosphorescence lifetime imaging if you have a molecule that is sensitive to that. So again, in the presence of oxygen, as labeled on the top there, these are microscopic images. And then within these images, histograms of the delay time are made. These are shown in the lower graph. And if you look at peaks in these histograms, so the main decay times, you can see that it shifts to higher decay constants for higher oxygen modifiers. All right. So another related mechanism related to this phosphorescence of this metallic porphyrin is so-called photodynamic theory. I just want to show that briefly. So the situation here is the same. We have this molecule with a triplet energy state. We have oxygen present there in the environment. So if we excite this metallic porphyrin, due to this whole process, the oxygen that is normally in the ground and the triplet ground state gets excited into the singlet excited state. The singlet excited states of oxygen is pretty reactive, so it will bind, for example, to DNA molecules, and it will actually it is actually able to break these DNA molecules. So based on that, this so-called photodynamic theory therapy is devised. So what happens is you inject a chemical into the body. So the chemical will be this metallic porphyrin, for example. That chemical hopefully accumulates at the tumor site. There is I told you this tumor is in a hurry. It will grow. It tries to grow, so it makes a lot of vessels around around the tumor site. And because it is very so much, these vessels are a little bit leaky. They're not perfect vessels, they're just a little bit messy. So after some time, these chemicals will accumulate at the tumor. If you then switch on the light, then this whole process is started. So the chemicals are activated by the light, and then we generate basically if you have enough light, you generate singlet oxygen at this tumor site, and that singlet oxygen will attack the DNA and will destroy the tumor. The good thing, or the promising thing about this approach is that it is doubly selective. You have a chemical that you can inject in the body and that will accumulate at the tumor site, but it still it does nothing if you don't illuminate it with light. Only when you illuminate it with light, it will get active and you will get some treatment. So you have double selectivity, the chemical itself and the light that you shine. Two more processes describing the phase of absorbed energy. The first is Rayleigh scattering, electric Rayleigh scattering. It's not really, it's a little bit strange to call this an absorption process, but what happens in terms of this energy diagram is that a photon is absorbed not to a fixed, not to a real energy level, but to a so-called virtual energy level, and it immediately emits a photon the same wavelength while relaxing back to gas. So it's a very rapid sequence of absorption and emission. And the only effect of that can be that the new photon has a different direction than the incoming photon, and that's why we call it scattering. It's a change of direction. But the wavelength, the energies and the wavelength of the two photons are the same. Involving these virtual energy states, there can be two variants of that, shown in the Bronsted diagrams over here. So again, the molecule is excited to a virtual energy level, and immediately a photon is emitted again. But now, in this case, it is not falling back to the ground state, but it's falling back to an excited vibrational state. So that means that the photon that is emitted here has a slightly lower energy than the excited states, and longer wave. This is called Raman scattering. In this case, because the liquid photon has a lower energy, it's called Stokes Raman scattering. We can also have anti-Stokes Raman scattering. That is what happens when the molecule already happens to be in an excited vibrational state. Then it gets excited to this virtual intermediate state, and you have the extension back to the ground state. So in that case, the energy of the emitted photon is larger. Therefore, the wavelength of the emitted photon is less. That is then called anti-Stokes Raman scattering. All these three processes more or less have the same space-time diagram, because nothing really happens, or everything happens really fast. So there is absorption of a photon, and there is immediate emission, instantaneous emission of a new photon. Again, the directions of these new photons are randomized, so they do not necessarily correspond to the direction that the incident photon has. So that's why they count as a scattering process. All right. One side note. In all of these processes, so with fluorescence, we have phosphorescence, we have Raman scattering, Rayleigh scattering. A new photon is generated. The photon is generated. So you could lump all these effects into something called spontaneous emission. So regardless what happens in order to cause it, all of a sudden you have a photon. So basically the random generation of photons in time. So the funny thing is that semi-classical theory cannot explain spontaneous emission. So semi-classical theory would give a quantum treatment to the materials. So that means you would have to solve Schrödinger's equation for that material. But if you solve Schrödinger's equation for an excited molecular state, it is stable. There is no reason why it should deteriorate back into the ground state. So you could have emission of a photon and then go back to the ground state, but equally likely would be that you have absorption of the photon back into the excited state. So the spontaneous emission, when it occurs, spontaneous excitation should also do that. So only for quantum electrodynamics came along, then we could adequately describe this process because then you have to also include quantum description, the quantum description of light as well. And then it works. But this is a brief set. Okay, so now let's look into how we can use this absorption processes for diagnosis. So this is one example. The example on the left you probably know pretty well. It's a pulse oximeter. It's this little clip that you get around your finger and that measures the oxygen saturation, for example, in patients in hospital. The other one is an optical method to measure bilirubin in newborns. I'll get back to that a little bit, to that specific application a little bit later, but also based on the absorption of light in the tissue. So basically, the sequence of events is we measure a signal, we extract the absorption coefficient, or the absorption spectra, based on a theoretical signal model, or theoretical signal description of our apparatus. And then we try to translate these absorption coefficients, these absorption spectra, back into to the physiological parameter that we're interested in, for example, oxygen saturation or bilirubin levels. And again, this is just a version of having a model that describes the tracks pretty well as a function of the dragon, but now we measure the tracks and what we want to ensure is tracked. So again, this inverse problem is at play. Okay. So one question, if we want to tackle this process and tackle this problem, is that we have to decide at which level we are going to describe this absorption process. So we can describe it in terms of the whole vasculature. So that would mean, for example, we would illuminate a large piece of tissue and we would collect light from all kinds of angles. So then we would have a lot of absorption going on at different locations in the tissue, and the answer that we would get would only relate to the bulk. We could also zoom in further, for example, the absorption properties of a red blood cell. So then we would study the light absorption properties of this single cell, but in the end we would have to do a measurement in tissue. We would have to translate or scale up, if you want, the results from that intermediate stage to the vasculature. And from a theoretical point of view, we could also start with the molecule. We could start with the absorption properties of a hemoglobin molecule. Then, if we have that, then the question would be, okay, how would that translate into the absorption properties of a red blood cell? And then after that, how would that translate into the absorption that you would measure on a piece of tissue? So as you reckoned a little bit from this introduction, we're going to start at this molecular level. So let's say hemoglobin, see how the absorption works there, and then later in a few steps try to scale that up to cells and to tissue. So first some definitions in order to describe it. So let's say we have this molecule over here. It is illuminated with an intensity I0 units watt per square meter. And also assume that this molecule, even though it is very complicated, of course, let's assume it has a geometrical cross section given by G. So that is in units of square meters then. We can then calculate the incident power on this molecule by multiplying the intensity, watt per square meter, with the area of the molecule, square meters, and then we end up with watts. So that is the power that is incident on this. And now also let's say that there is absorption takes place. So the amount of absorbed power, we don't know yet already, but let's say the amount of absorbed power is P sub A. Then we can calculate the ratio. The ratio of absorbed power over incident power, and that is called the absorption efficiency. So this is a property of the molecule, the absorption efficiency. Now next, if we calculate, so we can rearrange these equations a little bit. So the absorbed So the efficiency is the absorbed power divided by the incident power. That means that the absorbed power is the product of incident power and efficiency. And again, the incident power was the product of the incident intensity and the geometrical cross section. So we can write the absorbed power as this product of three terms: efficiency, geometrical cross section, and incident intensity. Then group together the product of absorption efficiency and the geometrical cross section, and we get a new cross section called the absorption cross section. So the efficiency was dimensionless. The geometrical cross section, of course, has dimensions of square meters. So this product is the product of dimensions of square meter. The absorption cross section. Now, since the absorbed, you can guess what it says there. Since the absorbed power is always less than the incident power, you cannot absorb more light than this incident. Since the absorbed power is always less than the incident power, that means that this absorption cross section is always going to be less than the true geometrical cross section. So these were quantities that related to just one molecule, the absorption efficiency and the absorption cross section. So now what happens if we have a bunch of molecules? So let's take a bunch of hemoglobin molecules. We put them in a cuvette. The cuvette is then filled with n identical molecules, and the volume of the cuvette is given by an area A. It's the illuminated area, and the length of the cuvette L. It's in the quadrant. So the volume is A times L, and also assume that the whole area of the cuvette is illuminated. There's light in the whole cuvette. So now the goal is to express the absorbed power by all of these molecules as a function of the incident intensity. Because we have these molecules and they're all identical, they all see the same incident intensity, they all see the same watt per square meter. So that means that the total absorbed power is simply n times the absorption cross section of a single molecule times the incident intensity. Or if you want, the total absorption cross section for the molecules in this cuvette is just simply the sum of the individual cross sections, the individual absorption cross sections. Okay. So we have n molecules in this volume of the cuvette A times L. So that means that number density, the amount of molecules per unit volume, is given by n divided by this V by this volume. The total absorption cross section was the sum of the individual cross sections. The cross section is n times the absorption cross section of a single molecule. If we now divide both sides of this equation by the volume V, we can define the density of absorption cross section, the density of total absorption cross section. So sigma A, big sigma A divided by the volume V is then n divided by the volume V times the absorption cross section of a single molecule, and this quantity is called the absorption coefficient. So the absorption coefficient mu of A is the density, the molecular length density rho times the absorption cross section. Physically, the interpretation is that is the density of absorption cross section. So this property is a property of not of a single molecule, but of a collection of molecules. Yeah. Okay. So now we have this cuvette filled with molecules. We have the cuvette has still the volume V, and there is still a number density rho inside the cuvette of molecules. And the light goes, the intensity goes in a straight line from through the cuvette. So now let's divide the cuvette, the length of the cuvette, into small segments that each have a thickness delta. Then the number of molecules in each slice of the cuvette. So we have n molecules. Total cuvette, there was global number density of rho, so that means that the number of molecules in each slide is now small caps n is the density times A times delta. The absorbed power in such a slice, so let's take a slice of the position L. The absorbed power in such a slice is the number of molecules in the slice N times the absorption cross-section times the intensity. And then combining these equations or adding these symbols, that means that we can write it as the number density rho times the area times L, the thickness of the slice, times the absorption coefficient times. Now intensity, so that would be the absorbed power. The absorbed intensity is then found by dividing this expression, this total expression by the area A, so it will drop out. Is the change in intensity when passing through this little slice L. So the cleaned up version is given change in intensity when passing through the slice. So change in intensity can be written as intensity after the slice and intensity before the slice, written like this. Now, of course, if you bring delta L to a very small number, you can write this as a differential equation. So there's dA, the change in intensity, is divided by dL, the length of the pipette. It's a reduction, so there's a minus sign in front there. And that is then written as the product of the density times the absorption cross-section times intensity. And again, we can combine density and absorption cross-section into the absorption coefficient. Okay. This differential equation is very easy to solve. The solution is an exponential, and the solution probably referred also before is called Lambert-Beer's law. So the intensity traveling through the cuvette E as a function of L is given by E0, is the incident intensity, and then an exponential decay with the absorption coefficient as the decay factor. It's called the law of Lambert-Beer after two contributors, both Lambert, the French, Lambert, the French position, and Beer, the German one, European collaboration and Van Letter. They both contributed. I think Lambert was the one who noticed that the absorption was dependent on the concentration of the molecules that you put in, and Beer was the one who found that if you made the cuvette longer, that also changed the absorption. By that you measure could also be the other way around. I don't remember. At least both combined it. Incidentally, if you're familiar with the German literature, then it's usually called the Beer-Lambert law, and if you have French literature, then it's the Lambert-Beer. Okay. So Beer's law. So in the example that I showed you that we discussed now, when you have transmission through a cuvette, but you could also have transmission along a very weird path of light in tissue. So here you would have light that is incident on tissue, and it travels to a location L1 where it is scattered, and then to a location 1 where it is scattered, and then to a location 2, and then to 3, and then to 4, etc., etc. These are all quasi little cuvettes, but they're inside the tissue. So you can apply this Beer's law along this path sequentially. So UA times L1 plus L2 plus L3, etc., etc. So it applies along this weird path. And if you have many of these weird paths inside your sample, then it also applies. So on the right hand side, it's a little bit complicated. You have two experimental configurations. The figure A has a fiber that injects light into the tissue, and another fiber that collects light. And then these little random trajectories represent all possible trajectories that the photons can take, going from this one fiber to this other fiber. So we have short paths that go more or less directly. We have longer paths that go weird long ways. Then in the other graph, it is only one fiber that both injects and collects the light. So you have also a lot of paths that can be differently shaped. The point is, you can apply the Beer's law along each of these paths. So it gets a little bit complicated to write them all like this. So now we have this, we have a distribution of path lengths, P of L, and each of these L's, you can apply Lambert-Beer's law against. So if you add them all up, the summation becomes an integral if the distribution is broad enough. You can write integrals like this. So the absorption takes place along the path of the photons, and it also means that you can apply Lambert-Beer's law along the path of photons. So, in summary, for this part, we have a single absorber. We can define the absorption efficiency as the ratio of absorbed power over incident power. That's an efficiency factor which is less than 1 because you can, less or equal than 1 because you cannot absorb more power than is incident. The absorption cross section is then found by multiplying this efficiency by the geometrical cross section. Again, the absorption cross section is then always less or equal to the geometrical cross section because of this conservation of energy principle. If you have multiple absorbers, you can define a new property, the absorption coefficient, like that. The absorption coefficient appears in Lambert-Beer's law. The intensity is an exponential decay with the absorption coefficient as a decay parameter. One more small definition: the product of Bmo times L is then again dimensionless. It's called referred to as the optical density. And then the important point is Lambert-Beer's law. Beer's law can be applied along the path. So if it is in a cuvette or in this strange trajectory, just along the path, the light is absorbed. Okay. In one of the first slides, starting with the topic I showed was this baby with this instrument to its head, which was called a bilirubin. So bilirubin is a breakdown product of hemoglobin. Hemoglobin is, of course, the protein that transports oxygen in your blood. And normally it binds to albumin. This is another protein. That combination is then transported to the liver, where enzymes break it down, and the breakdown products are then excreted. Now, in newborn babies, early born babies, this pathway, and especially babies that are born prematurely, this whole Pierce pathway may not well be fully established, fully developed, which means that the bilirubin is not cleared.
This also happen in people who have failing kidneys. Doesn't their skin also tend to turn a yellowish color?
Yeah, I don't know exactly what the mechanism for that is, but yeah, that also happens. Yeah. So in these babies it can also happen, and especially if the birth was a little bit, let's say, difficult, then also a lot of blood is hemolyzed, a lot of blood cells are squashed, so there is a lot of hemoglobin that is then broken down into bilirubin. So it can be, especially for preterm babies just after birth, there can be a lot of bilirubin present, which will not be sufficient to clear. That's then forced into the skin, that migrates into the skin, and that gives this yellowish color, kills it. Jaundice. Now the lucky thing is that bilirubin just breaks down under UV illumination. So what usually happens is that these babies, when after birth, are put in kind of a solarium under a UV lamp, and then the bilirubin is broken down, and really nothing, really no problem exists anymore. So that's great. But not always. You can have babies can have severe jaundice that lasts a couple of days, and that can be dangerous because too high levels of bilirubin that too high can cause damage to the brain. So basically, we would really like to be able to measure bilirubin concentrations after birth, following up, just to make sure that it does not get too high. The method for this currently is by taking blood samples and just putting the blood in the blood analyzer. That gives you the bilirubin content. That is done through heel pricks. So a little prick in the heel where a little bit of blood is drawn and then analyzed. But if the baby is really at risk for developing this, then this is done a couple of times a day, which you can imagine for a small baby. Even though it is a small amount of blood, it is still pretty it is still pretty impactful. So for especially for these cases, we would like to have a non-invasive way of measuring this bilirubin levels to replace or at least reduce these heel pricks. And that is where the optical method comes in first. So if you can look at, if you look closer at bilirubin, then this is the molecular structure that's not so important for this application. What we do know from that is that the molecule has approximately a diameter of about 1 nanometer, so it's a small molecule. The absorption coefficient, the absorption spectrum of bilirubin has been measured. You can see that in the graph here as a function of wavelength. What is shown here on the axis is the so-called molar absorption spectrum. The molar absorption coefficient is the absorption coefficient per molar of the compound. So we find that it has an absorption peak at 450 nanometer, so in the greenish light, where it has a molar absorption coefficient of 50,000 per centimeter per mole. At typical concentration, typical John's concentration, where people are getting worried a little bit, is around the molarity of 0.2 millimolar. If you look up the molecular weight, etc., of the hemoglobin molecule, it corresponds to about a concentration of 10 to the 17 molecules per cubic centimeter. These are then the numbers that we would like to be able to detect, because if we can have sensitivity to these levels, then the measurement could work. So my question to you now is that if you have me stop talking for now a little bit and we're doing something, can you now, using these numbers, can you now calculate the absorption coefficient, the absorption cross-section, and the absorption efficiency of bilirubin at 450 nanometer using these numbers? Any ideas for the absorption coefficient?
Thank you, John. Absorption coefficients. What I would do is we have the molar absorption coefficient, we put right there, and we have the amount of mole that becomes a problem. So all you do is simply multiply one with the other. Then you get the please multiply one with the other, then you get the absorption coefficient for this specific case.
That is correct. And
That should come out to, if I'm not mistaken, to around 0.1 per meter.
yeah, 10 centimeter. Yeah, that's correct. Okay, is that clear for everyone? I guess so. Okay, then the second one, from that, can we calculate now the absorption cross section of such a molecule?
Right.
Yeah, go ahead.
Right. Similar process you previously explained to us how you could get the absorption coefficient from the cross section, and you just switch that around. You need the density for that. So the cross section will equal the absorption coefficient divided by the density. You have the density, so all you do is that 10 per centimeter you just got, you divide that by the, I believe it was 10 to the power of 17.
Yeah.
Yep, and then you get 10 to the power of minus 70, minus
60.
Okay.
Yeah.
It will be 10 times 10 to the power of 17, which would be 1 times 10 to the power of minus 6.
Exactly. Yeah, in square centimeters. Okay, and then for the efficiency, I'll take that one. For the efficiency was the product of the cross section was the product of efficiency and the geometrical cross section. And we knew that the diameter was approximately 1 nanometer. So that means that we can calculate an approximate area of the molecule of this value, and then find that the efficiency is in the order of, this one's away again, is in the order of 1.33 to the power 10 to the power minus 2. So basically that means that the efficiency is in the order of 1%. The absorption efficiency is in the order of 1%. So that begs this question. So this would be the absorption efficiency that we want to detect. But of course, bilirubin is not the only not the only absorber in the tissue. And the competition in this case is given by blood. The blood that's also present there. And on the bottom side here, you see a graph that plots the absorption efficiency of hemoglobin and oxyhemoglobin. And if you then look at 450 nanometer, which we were considering, then 1% sits about here. But the absorption efficiency of these blood species is much higher. So that means that for every photon that you put in, it's much more likely that it's going to be absorbed by hemoglobin than by bilirubin. Still, we were trying to measure these bilirubin levels. So can you think of a trick that we could do to still, given this huge background of absorption by hemoglobin, can you think of a trick to still extract this small level of bilirubin?
Maybe some mission times, like again, mission times
Yeah.
different measure different wavelengths.
Yeah, that's the most simple. That's the simplest trick to do it. Because if you would measure it 450, you would measure the combined effect of bilirubin and hemoglobin, which is then dominated by hemoglobin. But if you would do a measurement, say at 700 nanometers, or maybe 800 nanometers, then the bilirubin does not absorb at all. There is no absorption. So all you would measure here is due to blood. So if you would be able to do a couple of measurements here, that would allow you to calculate the amount of blood that is in there. Then you could correct the measurement at 450 nanometer And for that blood transfusion, and extract then what the bilirubin absorption is. Yeah, so the answer in this case is do a spectroscopy measurement, measure at multiple wavelengths, and then some clever calculations to extract the absorption frequency. Okay. Let's take a brief break, 10 minutes again, and then I have a few more slides, and then that's it. Yeah. Oké, laatste loodjes. So this is the result that we have so far. We have an experiment with cuvettes, incident intensity on one side, detect intensity on the other side, and Lambert Beer's law applies to the geometry. The substance in the cuvette has an absorption coefficient, which is the product of the density and the absorption cross section of the molecules. Lambert Beer's law. Okay, now let's go. Now let's turn this around a little bit. So let's say we have the same experiments. We have molecules that are homogeneously distributed. We know rho, and we know sigma, and we know the density, and we know the cross section, and we know the dimensions of the cuvette. My question is, what is now? So let's do this experiment. What is now the transmittance in this experiment? So the transmittance being E over ECR.
Is that sort of the absorption efficiency of the entire
Funnily enough, that is kind of the way I want to go, but not yet. Sorry, maybe this sounds a little bit too much like a trick question, but it is simply just Lambert Beer's law, but then rearranging a little bit. So we had Beer's law that E is E0 times the exponential decay. So now the value is zero is simply this exponential thing. Right? So it is just Beer's law. Was my question. The follow-up question. So this is what we will do in experiment. If we do the experiment, we would measure this transmittance. So now the follow-up question is, if I did this, and it's also not a trick question, it's just the answer is almost staring in your face. If you would want to retrieve the absorption coefficient now from such a transmittance experiment, what would we need to do?
Yeah, take the logarithm and some like divide the other factors.
Yeah, you take the logarithm and you know L, and so you can divide by it. So that would be the experimental approach. That would be the you would do a measurement before the cuvette, after the cuvette, calculate the ratio. That would be the transmittance. You would take the natural logarithm of the transmittance and divide by L. And that would give you your measurement of the absorption coefficient, your estimation of the absorption coefficient. Okay, is that now this was too simple. Now let's make it a little bit more difficult. So let's say by some kind of magical trick, we were able to push all the molecules in the cuvette to the front side in such a way that they take up the first half of the cuvette. So we had a cuvette where the molecules were all homogeneously distributed, but now by some magical trick, thought experiment, we are able to push the molecules to the front side of the cuvette, the front half of the cuvette. What is the transmittance in this case?
Isn't it the same as before?
Yes, it is the same as it was before, but can you elaborate a little bit on that answer?
Is it again
Just do the same thing with higher density and then a smaller error.
Yeah, that's exactly the answer I was looking for. So we have, because we pushed all the molecules to one side, the density is 2 times as high, but because they are all in half of the cuvette, L is also twice as small. And these two factors cancel. So in the end, you would end up with the same transmittance. So then the question is, what would be the absorption coefficient retrieved in this experiment? Yeah, the same, would be the same, because then you take the logarithm and you divide by L. You take the logarithm and you divide, let's assume you did not know that this happened, you still divide by L of the cubed. So that gives you the same answer. Okay, yeah, same answer. Now let's do another magical trick where all the molecules are pushed to the side of the cuvette. What would be the transmittance in this case?
in this case, the L will be unchanged, but the density we have, we have on one side, double in the other.
Actually, it would be 0 on that because all the molecules would be pushed. Yeah. So it would be doubled on one part, on side of the kit, and it would be halved on the other one. Now it's unchanged. So if you would, so the total transmittance, ELB0 would be a half for the part of the cuvette where the light goes straight through, and a half times the Beer's law, but then with double the density on the right hand side. So that would be the expression for the transmittance. Now, what would be the absorption coefficient retrieved from this experiment? So again, what we do is we take, if we do the experiment, we have no idea what was going on in the cuvette, so we just take we take the same procedure. We take we do the measurement, we measure t, we take the logarithm, and we divide by L. So what we would measure in this case is this kind of complicated expression over here. But for any type of number that you calculated, it is going to be less than what we measured in the very first experiment. So even though we have the same amount of molecules in the cuvette, what we will measure here as an absorption coefficient is less than what we would measure in the original experiment. So not the same answer. So the conclusion from this thought experiment is that the results what we will measure is it kind of depends on the organization, we call it organization of the molecules. If they're homogeneously distributed versus they are packed to one side of the cuvette or maybe packed to another side of the cuvette, you get different answers. So that is something that we have to take into account. We have to take into account because what we did for now is that we considered absorption by hemoglobin molecules, not just molecules in the cuvette. But in real life, these molecules are packed together in red blood cells. So we have parts of the tissue where the hemoglobin molecules are inside the red blood cells, and we have parts of the tissue that aren't outside the red blood cells. And to make matters worse, in tissue, the red blood cells are contained in blood vessels. So again, we have regions where the molecules themselves are present and where they are not. So this organization that gives you different answers will also be at play here. So that means that it's not entirely straightforward to go from the absorption properties of these hemoglobin molecules to the absorption properties of, let's say, white vasculature. So that's the point. This is just what I said without the picture. So it happens in molecules, and it also happens, for example, in melanosomes. Melanosomes are the granules that are in your skin. They are also the absorbing compound is contained in particles in cells. Okay, so let's try to get a grip on that. So we now have to be very careful about what we call it. We now have two densities. We have the density of the absorbing molecules so the number of absorbed molecules inside the particle, that is the molecules, and we have a density of the particles, which is the red blood cells. So that would be the total number of cells within a larger fluid. So we have two densities. So the one for the molecules is labeled with M, and the one for the particles is not. That's first. Then just a brief sidestep for notational purposes. So rho was the number of particles per unit volume in the total measurement volume. That is equal. So rho is equal to the ratio of the volume fraction, Fv, divided by the particle volume. And you can see that as follows. The volume fraction as percentage or as fraction is given by the total volume of the particle. So it's n times the volume of one particle divided by the measurement volume, n over v is rho. That's it here. If you then rearrange that, and you get this expression, this equality rho the density is equal to the volume fraction divided by the volume of the particle. Just keep that, put that somewhere on the sideline of your notes, because it's volume fraction. In the case of blood, the particle volume fraction is usually called the hematocrit. Just that you know. Okay. Now let's say for simplicity that this red blood cell, this particle where the molecules is cubic. It's a little bit. So it is a particle with volume V. So P cubic at size R, so R times R times. And it's filled with molecules with known absorption cross section and with a certain density rho. And we assume that Lambert-Beer's law holds for this whole particle. So if we would shine light to one side of the particle, measure it from the other side, we could use Lambert-Beer's law to calculate the transmittance. So there we go. If we have an incident density here on one side of the particle, what will be the transmittance if we measure it on the other side of this one particle? So basically, the particle not just behaves as a cuvette. So again, Beer's law. Again, the transmittance would be E divided by E0 would be Beer's law. So we would have rho m here, the density of the molecules, the cross section of the molecules, and now the length of the cuvette, the length of the particles. So this would be the transmittance. So if we have this incident intensity and this detected intensity, what are then the powers that are incident and transmitted for this particle? Intensity is watts per square meter, and power is in watts. If we have something in watts per square meter, what do we have to multiply it to get to watts? Yeah, which is an area. R squared. Yeah, it's just so the intensity E is incident on the face of the particle, on the face of the cubicle, and it has a size R squared. So the incident intensity will be I0 R squared, and the transmitted intensity will be I. Okay. What is then the absorption efficiency of this particle? Think back of your definitions. What was the definition of absorption efficiency?
The amount of absorbed light over the fraction of light absorbed compared to the fraction of light that was sent through. Calculate that.
How was that? So a little bit.
It would be PT over P0.
Yeah, PT over P0. So the no, not PT over P0. It would be PA over P0. So the absorbed power divided by the incident power. But they are. That's no problem because we have conservation of energy, the absorbed power is equal to the incident power minus the transmitted power. So Q, the efficiency of the particle, would be the absorbed power divided by the incident power, would be equal to P0 minus the transmitted power divided by the incident power. So this one, this part levels cancels out to 1, and for that part we can use Beer's law. So that is the exponential term over there. So the expression for the efficiency, the absorption efficiency of the particle is then 1 minus exponential UA times 1. Okay. And remember, this is the UA that is in there is the absorption coefficient of the molecules inside the particle. Okay. If we now define an absorption efficiency, can we then also define an absorption cross section for this particle? So again, think of the units. The absorption efficiency was dimensionless. The absorption cross section has units square meters. Yeah, so we have to multiply it with an area, and in this case that's the area of the particle, so multiply it with r squared. So the absorption cross section of this particle would be well, the expression on the right hand side. Okay, well, let's continue. If we have an absorption cross section, then we also calculate an absorption coefficient, provided that we know the volume fraction. To the sideline of units. So we know the volume fraction, hematocrit, it was blood, and we now calculate the absorption coefficient. How do we go from absorption cross section to absorption coefficient? To go from absorption cross section to absorption coefficient, we need to multiply with the density of the particles, rho. But rho was equal to, that was the previous slide step, was equal to the volume fraction divided by the particle of the volume. The volume of the particle. So that means that the absorption coefficient is rho times the absorption cross section of the particle, is volume fraction divided by particle volume times the absorption cross section. The volume, of course, is r the third power. So we can combine these equations. R squared cancels with r squared there, so it's 1 over r. So we end up with this expression for the absorption coefficient. UA for this particle, or for a bunch of these particles, is the volume fraction divided by the size of the particle times this fraction. So basically, this is the result of this whole organization, because we now contained the absorbing molecules inside the particles. This is an expression for the absorption coefficient that we would measure in such an experiment. Now let's get repeating some questions. Now let's get destructive. So we did a lot of trouble getting these molecules inside the particles now, and they're contained in the cuvette. Now let's just break all these particles so that all the molecules become free floating again. What is then the absorption coefficient that we will measure? There are no particles anymore, so there's not going to be a volume fraction, not going to be a particle radius involved anymore. So all the molecules that were first contained in the particles are now homogeneously distributed in the cuvette. And when we do the measurement,
Absorption that stays the same, right?
The number of molecules.
Oh, yeah.
But what you will measure is going to change because you now they're no longer contained in particles.
So if that's the case, then the density would decrease by a factor of the volume, would decrease by a factor of the volume fraction of the of the total. Okay, so they were captured in particles, and now the particles are open, but the particles do not take up the full volume of the what do we call it?
So the cuvette.
The cuvette, yes. And so it would, the density would decrease by a factor of whatever the fraction of volume that the particles took up within the cuvette.
Yeah, and that is the volume
That
fraction.
is the point.
And that is the volume fraction. Yeah. So that is and it's a fraction less than 1. So the absorption coefficient gets a little bit less. So we had an absorption coefficient inside the particles that is now diluted by a fraction, volume fraction. So what we would measure there from these molecules now free in the solution would be this. So we have a substance that has an absorption coefficient, a bunch of molecules that have an absorption coefficient μ. If I contain these molecules all in particles with volume fraction f v, and I would do a measurement of the suspension, I would measure that. If I then would break all these particles again, and I would do a new measurement, I would measure these with the molecules in solution. So I would get two different answers for the same, even though I would have the same amount of molecules. The funny thing is that so these are the two equations then. If I take a ratio of these two, so the ratio of the molecules in suspension over the absorption coefficient of the molecules in the solution, then the volume fraction even drops out. So it's just a function of the particle size and the absorption coefficient of the substance in the molecules. This effect is called absorption flattening. Why flattening? Because the absorption will appear lower if you put it in in particles. So it's flattening. Important to note that there are 3 absorption coefficients involved in this. So there's the absorption coefficient that you would measure if you would do an experiment just on one particle, so of the substance that's in the particle, and these two are the absorption coefficients of a bunch of these particles in the cuvette, or all the molecules taken out of these particles in that. So it's 3 different if you write that specifically for blood, then the suspension would be where the molecules are in red blood cells. So that would be the absorption coefficient of blood. If the molecules were outside the red blood cells, then they would be in just a hemoglobin solution. So here the solution would be hemoglobin solution. And then the absorption coefficient that is in the factor is the μA of hemoglobin inside the red blood cell. Absorption flattening, other term that has been coined in the literature is pigment packaging. So you have this absorber, this pigment, and you package it into a particle, so pigment packaging. There we go. One funny thing is, if you look at the year of this publication, it's 2004. So it is really amazing that this effect has been overlooked for such a long time. So what people have been doing is reason. Okay, it is very difficult to. So blood is really tricky stuff. So it's really difficult to measure something optically on a blood cell. So what people usually do is say, okay, let's squash these red blood cells, then we make this nice hemoglobin solution, and there you can do the experiment. And then, so people did that, absorption measurements of different hemoglobin solutions of different concentrations, and got a bunch of free spectra, and then they just scaled it back up to blood without taking into account these effects, and only in the big light of things very recently. people have realized again that that's not correct. Sometimes it's really nice. Okay. Can we now scale this up to the vasculature? So we had hemoglobin molecules contained in red blood cells. We have also red blood cells contained in vessels. Yeah, why not? So we can do that basically following the same steps. We can calculate a absorption efficiency for tissue and divide it as the amount of power absorbed by the tissue volume divided by the power incident on it. You can go through the whole analysis again just by replacing the size of the red blood cell by the size of the vessel. And then you get a similar expression for the absorption coefficient where the blood is contained in vessels. So there is an inhomogeneous distribution of red blood cells divided by the absorption coefficient where the red blood cells are homogeneous in tissue. So the scaling should just work just. I want to show you a final example. We a couple of years ago, one of our PhD students did. When finally we had this all figured out, we took all these spectra from the literature, tried all these measurements at different concentrations, and tried to scale them to a common level of blood, so calculate the absorption coefficient of blood, but then taking into account this effect of pigment packing. So here on so what you see, these two graphs are literature spectra that are taken from literature. The source spectra are here, so we have measurements that were taken at 5% dilution, at 33%. So it's a huge range of different experiments. So they were all scaled back to the common concentration here, 45% hematocrit, so it is almost to the concentration of red blood cells in blood for let's say a healthy man. It's a little less. So this for oxygenated hemoglobin, it would look like right hand side for deoxygenated hemoglobin, and then you can compile these. You can calculate the weighted average of these spectra and end up with this. So this would be the average, the black curve, with a little spread because of the different spectra found in literature of the absorption coefficient of all that. Somehow, yeah, very nice. Okay, so brief summary again. So we calculated the absorption coefficient of suspensions and solutions. They were different. We have an equation for the absorption of suspension in terms of volume fraction, the size of the particle, and the absorption coefficient of the substance that is in the particle. Same thing for the solution. Calculate this ratio. This ratio expresses an effect that is called absorption flattening. That's it for today. But what I would like you to do is I've put on Canvas these book chapters. That is from a book on biomedical optics. I'd like you to read chapters 1 to 3. You don't have to necessarily read the whole thing before next Friday, but I do want you to read them as we go along. So there will be some stuff that we covered today. There will be some stuff that we'll cover later on, but keep in mind that in the end, I will shoot it back. What I would like you to know before Friday, because we can discuss it then, is go to this website. That will lead you to a group of our colleagues in Oregon, where absorption spectra of oxygenated hemoglobin, oxygenated and deoxygenated hemoglobin are compiled, just like in the literature. And that page ends with a calculation of the absorption coefficient of blood. So it will give you spectra of the absorption coefficient of blood in verse centimeters. However, it does not account for this absorption flattening. So apparently it was compiled before 2005. So what I would like you to do is take these spectra, so you can just download them as an Excel file from that site, and then use the correct way of calculating the absorption coefficient of oxygenated and deoxygenated. So just based on that. And the really fun thing would be if you produce graphs or you have spectra, so you can really visually compare what happens to the absorption coefficients of solutions versus suspensions. Okay, try that, and then I hope we can look into that starting Friday. Have a nice day.